Hi, hello everyone. Let me figure out how to get my thing on screen. Oh, that's pretty good. Let's just figure out how the mouse works. Okay. So we're going to do this one, view full screen. Okay. So now we can get going. Hello, hello. My name is Bryan Boreham, as Julius was just saying. And so my talk, I sort of changed the title. I called it, Dude, Where's My Memory? And then I thought that's not inclusive. So Prometheus, where did my memory go? This chart on the right here is sort of approximately the point where I decided to fix one bug in particular, or to sort of say where, because it hit 400 gigabytes. I don't know if you can read the text, but this is one of our production Prometheus in one of our largest clusters, and it hit 400 gigabytes and crashed. And anyway, we'll tell you a little bit about how we got there. Yeah, I should say a little bit. I work at Grafana Labs on what we call the databases. We store things in our cloud service and use with several open source projects. So we store metrics in Mimir, we store logs in Loki, we store traces in Tempo, and we run a lot of this. We do all of our monitoring on our own system, Mimir, which holds all of the metrics for everyone. So it might be a little weird, like, why do I care about Prometheus? Well, we run Prometheus as a backup because we're sort of afraid that our own tool might fall over. And so we run both. And the point of Mimir is to be horizontally scalable. You can spread the work out over many, many computers. But Prometheus is vertically scalable. Everything has to fit in one process. So let's see, I guess some of you must experience this. So who runs Prometheus? Nearly everyone. Okay. Keep your hand up if you have a Prometheus bigger than 100 gigabytes. Oh, lots of people. Like a third of the audience, 100 gigabytes, nothing. What about the one I had, 400 gigabytes? Few? Okay, who's got bigger, who's got one? Keep your hand up if you're bigger than 400 gigabytes. There's one, okay. So this talk is for you. Oh yeah, one thing. I met someone outside who wanted to know why his exporter was taking so much memory, and sadly, I'm gonna have to do that talk another day. This talk is about Prometheus the server, where that's what I'm talking about today, not the exporters. Okay, so another bit of history, recent history. So this was Ganesh, very pleased that our, this was basically the 400 gigabyte one had come down by half. And the reason for that, and this was released in 2.39, and the reason that came down was I fixed a bug in the TX ring structure, which I'm not going to talk a lot about, but those of you who have really, really big Prometheus, you may find that this one bug fix helps a lot. So you're welcome. A little bit of kind of setting the scene. I guess most of you will be very familiar with this picture. I'm going to kind of refer to these different functions of Prometheus. So I wanted to put like the big picture on the screen. So the basic idea is that Prometheus does this scraping operation by which it fetches metrics either from your applications or from exporters that get the data from somewhere else. It stores it on disk. it runs rules periodically, and it answers queries. So those are all the things that Prometheus is doing. And so the question is, when you have one of these really, really big Prometheus, why? Why is it so big? What is taking up all the memory? Does anyone have a guess? Which? The chunks. Okay. So one guess over here is the chunks. The samples, I guess. The individual metric samples, yeah. Well, we'll see. We'll see if that's true. Okay, let's take another little detour into what do we actually mean when we're talking about memory usage? You know, we know it's too big, but what actually is this number? So I think the most common one for people to look at is it says here working set. And this picture is flapping around 60 gigabytes. So this is not the 400 gigabyte one. I chose, this is the one that runs our ops cluster, where we run our internal monitoring, because I didn't want to fool around with production just to do a talk. But anyway, so this one's about 60 gigabytes. So everything I talk about in this talk is going to be kind of relative to that 60 gigabyte number. Yeah, working set is a number that comes out of the operating system, out of the kernel. And it is the kernel's estimate of how much memory your program needs. So this is a little bit weird. So let me kind of come at it from another angle. If I overlay on this picture what the Go program, the Go heap memory is using, so that's the yellow line, the Go memory is lower than the green line, the working set. Also, the Go memory is kind of flapping up and down, right? It's up, it's down, it's up, it's down. You know, what's going on? Well, a couple of things are going on. So Go is a garbage collected language. The Prometheus is using a certain amount of memory to store all your data for a long time. And then in the operations that it does moment by moment, it takes a little bit more memory and then throws it away, and a little bit more memory and throws it away. And that's the garbage. And the garbage builds up and then it gets collected. So that's why this line is flapping up and down. This particular server is garbage collecting about once a minute. So it's a little bit too fast to see on the picture. But effectively, that's what's happening. It's being garbage collected down to about 28 gigabytes, and it's going up to about 60 gigabytes. Well, sorry, 50 something. Up here, it's about 50 something. Yeah. So that's one thing that's going on. The kind of constant memory in use is about 28 gigabytes, and there's a lot of garbage being built up and collected and built up and collected. But we're still not kind of closed that gap between the yellow line and the green line. What else is in there? There's the program itself, right? The Prometheus binary is like 100 megabytes or something like that. It barely shows up, right? This is a 60 gigabyte line, so that doesn't really show up. There's a lot of memory mapped files that are anything older than a couple of hours old in Prometheus is in memory mapped files, which are not Go memory. But again, it's not a lot in that. It's kind of a chunk of that gap. But there's other things yet. There's the Go routine stacks. There's heap memory that's kind of wasted, what they call idle heap. It's not being used. And it's a very, very difficult thing to kind of nail down exactly where the memory is being used. And it's not helped by the fact that Linux is guessing where the green line should be. That's not like an accurate measure of anything. That's an estimate from the operating system of what it thinks the working set, what you really need. Maybe you do, maybe you don't, who knows. So I just wanted to stress, this is a very, very complicated question. How much memory are you actually using? and yeah, can be difficult to. In the 400 gigabyte one earlier, there were 70 gigabytes of idle heap, just to give you an idea of the scale of this potential problem. So, I'm going to drill in now. I'm going to look inside the Go heap. So we're going to take that 60 gigabytes, going to focus on the yellow bit, and I'm going to look at it using a heap profile with a visualization called a flame graph. So it looks pretty fancy, right? And it's like orange, and it looks a bit like a flame. That's why but it's going downwards. We kind of need to turn our heads upside down to see it as a flame. The way to read this is the width. The width of one of these bars is relative to how much memory is being used. So the bar at the top is 28 gigabytes. That's the whole of the Go heap, and it says root. So that's the sort of the root of everything in the heap is. In this particular picture, 28 gigabytes. And then it's divided down. We'll drill into that a little bit more. So the width is the really important bit in this picture. The height is just where one function calls another one, calls another one, calls another one. So the relative height's not that interesting. The names of the functions kind of tell us where the memory is in use. And we're going to kind of relate that to the functions of Prometheus as we drill in. Just to kind of flesh it out a little bit more, this is when it does the scraping thing, this is what it sees. So this is an example of the kind of data that comes in. So every metric has a name, it has some labels. These are the labels, label name method, label value post. And here are the actual samples over there. So, so having set all of the scene like that, I'm going to drill in to the bit that says scrape loop. So it's a loop. So we scrape, I think, every 15 seconds. It sits there. Every 15 seconds, it goes around everything in the system asking for the metrics. And the width of this bar is nearly 22 gigabytes. So out of the 28 we were looking at earlier, this is most of it. And the relative width tells us where all the memory is being used. So, top 10. So the number one, oh, not yet. There. Number one biggest use of memory inside this Prometheus, not chunks, labels. And I picked one Prometheus in our production system to look at, but I do this a lot. And I'm very confident that your Prometheus looks like this too. That pretty much a third of all of the memory in this Prometheus and everyone's Prometheus is in those labels, and that's that method equals post, status equals 200. You know, those things. That is what's taking up all the memory. Well, at least a third of it. Well, we'll get on to what can we do about it in a minute. Let's just run through what else is in there. Number two, you're almost right. The samples which are compressed into chunks, one of the reasons why they don't take up so much space is they're compressed, right? Prometheus uses a very sophisticated sample compression algorithm which came from Facebook, I believe, called the Gorilla compression algorithm. It's very powerful. It squeezes down the data very, very tightly for the samples. And so they, in this particular case, about 17%. And again, that's pretty typical, that it's not the biggest, it's already very, very compressed. And somewhat by contrast, the labels are not compressed at all. You know, it's kind of how we get here. What else is on this picture? So the series, meaning metadata about the series, like a pointer to the labels, like a pointer to the chunks, the out of order structure that Jesus was talking about, all of that data is another 14% in metadata. So it's really the data structures that are kind of managing the data are massively outweighing the data itself. It's kind of interesting. I mean, that's why I'm giving this talk, right? I think it's interesting to know that it's not the samples. What else? Scraping. So this is a pretty big Prometheus. It's scraping thousands of targets. And each one has a little data structure, and it sort of remembers what it saw last time, and it tries to be efficient about that. It's got a timer running of when it's going to run the next scrape. So in this picture, that added up to 11%. The index. The index is another thing that kind of feels like it ought to be massive. It's another name for the index in Prometheus is the postings. That's kind of a traditional term for this sort of inverted index. But it turns out that's tiny in relative to all these other things. So let's take a look at the data structure just to sort of understand that from a different angle. So the series that I talked about, so if you, in your Prometheus, if you have, I think this one has like 12 million time series or something like that. So there are 12 million of these data structures called, in the code, it's called mem series. And each one has a reference to the labels, has a reference to the metadata, has a reference to the chunks. The TX ring was the thing that went wrong in the very first picture. That was the thing that blew it up to double the size. Sometimes, not always. But that's the thing that does isolation between reads and writes. So when you do a read, you don't see half of a write. That's what that's doing there. So if you have 12 million series, you have 12 million of these things, and that takes up a chunk of memory. The labels, so there's kind of two problems here. One is that every single time you repeat something like name equals requests, it is actually holding those strings again and again and again. That might seem kind of dumb. But it turns out it's quite expensive to try and do something different. I am working on doing something different, but not what you think. Interning, yeah. So I've spent like a very long time not implementing interning. That's another talk. It's not finished yet. One of the reasons is that in the Go program, each one of these strings has a header, and these headers are 16 bytes each. So actually, the work that I'm doing is focused on getting rid of these, because they're bigger than these. So that's kind of counterintuitive, but true. Anyway, so lots and lots of repeated strings, lots and lots of string headers. That's where all the memories go, are like a third of all the memories over here. The chunks, the samples are kind of different sizes for different chunks. And the out of order chunks go in here as well. Relatively small by comparison, because they're very, very compressed. And then a bunch of other things that I'm not going to go into detail on. So, just to kind of take a look at this from yet another point of view, the profile that I was looking at, you can ask it just to give you a textual dump. So this is just I won't go through that, but just to sort of view it, you can kind of see in very great detail if you look at it from this way around. The labels, the what is this thing? The metric. This is the this is the routine it was allocated in. This is all part of the same. Labels and metric are kind of two names for the same thing in the code. The series, the head chunks, etc., etc. So, so that's kind of the main point of my talk. Is I thought you'd be interested. Like, why is it so big? Well, that's why. And then I thought, well, you might also want to know, well, what can I do about it, right? Like, what can I make my Prometheus smaller? Well, you can hack on the code like I do, like, please. But it is hard work. What else can you do? Oh yeah, so one thing you can do is you can open up the this status menu on your Prometheus and get a better understanding of where all the memory went. So this is the status view on the one I was just showing you. Like I say, I had 12 million series, and that's where a lot of the memory went. And there are some more, as you scroll down this view, you get some more things to look at. Don't look at this one. It looks kind of good, right? It says high memory usage, but it says this thing here is 3.6 megabytes. Like, come on. 60 gigabytes. Tell me about 60 gig. This thing is just doing the wrong calculation. So sorry, don't look at that one. This one is more useful. So this is the name equals value pairs. And basically every single one of the series in our Prometheus has one of these pairs. So you can look through here and you could decide, well, I don't need some of that information. So you can write drop rules. You can write into your Prometheus config, into the metric relabel config, because there's one called relabel config. That sounds attractive, but that's the one that affects the things that are scraped. So assuming you're scraping all the right things, once you've scraped it, you can drop things. You can drop an entire series. Like in this example, we're dropping anything that has a namespace of testing or staging. So I'm not going to go into a huge amount of detail, but you can write a drop rule that takes out entire series or entire classes of series, or you can write a label drop rule that will just take out a few labels. And with that knowledge that it's the labels that are taking up all the space, you might want to go think about that, right? There might be some labels in your data that you're not that interested in. And in the current implementation of Prometheus, that's what's taking up all the space, so you might think about dropping some of them. Okay. One more trick. Have I got time? Yeah. So, you know, I was talking about the garbage collection, where the kind of real memory usage of my program was 28 gigabytes, but Go lets the heap build up to double that number, and then garbage collects it and lets it build up and garbage collect. So you get this kind of sawtooth that I've simulated it. I've blown it up a bit so you can see it more clearly. That's in my program. That's happening once a minute, but that's what's happening inside. That it's garbage collecting and then building up and garbage collecting. So you can set. So there's an environment variable you can set. It defaults to 100. It's called GoGC. And if you, for instance, if you set that to 50. Then instead of letting the heap grow to twice the size, which is 100%, it'll proportionately grow less than that. So the trade-off is it's running garbage collection faster, in this case twice as fast. So I think this is probably okay, right? Because generally the Prometheus is like really, really big in memory and maybe quite big in CPU, but not that big. And it's only garbage collecting once a minute, so now it's once every 30 seconds, right? it's not all the time. It's not like continuously trying to figure out what's going on. So that's a tip. You might want to try that. Don't go too far. Like, don't set it to 1 or something like that. It'll garbage collect every millisecond. Don't do that. But yeah, try setting it to 50 or 75 or something lower than 100. That's going to shrink that Go heap at the cost of a little bit more CPU. And that's something you can go home and try right now. Well, when the conference is finished. Yeah, it's an environment variable. If you're using Kubernetes, this is kind of how it looks. If you want to set an environment variable, if you're not using Kubernetes, you should probably know how to set an environment variable. So that's it. That's me done.
Thank you. There's a question way back there. Let me run around. Where was it?
So I know you said that string interning is a topic for a different day, but could you perhaps give us a teaser on why you decided to not look into it?
Yeah, so two reasons. Let me bring that data structure back up. So one reason is, so the idea of interning is you say, well, instead of having many copies of a string, I'm going to have one copy. And so you need a data structure to hold the one copy, and that data structure is going to be a bottleneck for concurrency. So that's my number one reason, is I didn't want to have to solve that problem. I don't argue that it's not solvable. I just didn't want to solve it. Second reason is this thing is in Go is 16 bytes. And this is 8. So I focused on saving 16 instead of saving 8. So that's there's a draft PR in Prometheus. I did not memorize the number, but it says store all the labels as a single string is the title. You can go look at the code. You can do something better. Please do.
Okay, thank you, Bryan. Like, amazing talk, and thank you for your work, like, on those optimizations. It's like everybody, wants that, and I think you kind of shown how to do this. So hopefully we have lots of contributions we have to then review, but it's amazing. My question is, like, you mentioned the garbage collection and how to tune this. And there is new option coming. I mean, it's already there through, I think, 1.18 or 1.19, Go mem limit. Have you played with that? Would you recommend using this against Prometheus?
Yeah, Go mem limit. I believe Go mem limit is new in Go 1.19. It will work in Prometheus, the last couple of releases. So it's not on this picture, but so Go GC is a relative measure. Go mem limit is an absolute measure. So you get the choice, right? You could say Go mem limit equals 50 gigabytes, and it would basically bring the sawtooth down to 50. But if you do something unusual, like let's say somebody comes and does a lot of queries very, very quickly, that's going to use more heap. So the trade-off is with Go mem limit, it's going to garbage collect faster and faster and faster, and eventually garbage collection is going to kind of take a lot of your time, and it's maybe going to slow down scraping. It's a little bit dangerous. So I'm recommending the relative measure. So if you beat up your Prometheus, if you really make it go fast, like do a lot of queries, a lot of work, then it will get bigger, because everything you do takes a little bit of effort. But it will everything will stay relatively the same. Whereas if you put this absolute limit on, which is what Go mem limit will do, there's a danger that you can break it by driving it into this mode where garbage collection is taking like all of the time. And I want to make one other comment. I did actually think, this is kind of steady state. I'm mostly describing steady state and what happens when you put a lot of queries in, or like a really long query or something like that. So I tried with this. This is why I wasn't using production. I tried to make the line, not this one, but the line from earlier, this line. I tried to make this line go up by doing queries, and it basically couldn't. Most of Prometheus is in the steady state. For one like this, one with 12 million series in memory, it's very hard to make it use a lot more memory with queries, because I did actually try in this picture. Well, there's one over here. You've been silenced. Cancelled. Try again. Keep
Does
trying.
it work?
Yeah.
Oh, okay. It works. You showed the picture with from Twitter screen with a memory usage drop. Yes, this one. And I didn't understand how did you achieve this from your slides. Could you explain?
This was a bug fix. So my talk was describing the normal kind of correct operation of Prometheus. This was a bug which I mentioned the TX ring, the transaction isolation between reads and writes. So if you had a compaction that took a really long time, then the TX ring would get bigger and bigger and bigger. Coupled with a kind of unfortunate way the Go memory manager worked, that was responsible for in this picture, like, I don't know what, it went from like 360 to 180, so like 180 gigabytes. There's two Prometheus on there. It's an HA pair. HA, I always like to put the scare quotes in HA. The reason why I do that, this is precisely the reason I do that. If you have two Prometheus doing the same thing, and your problem is that it runs out of memory, they're both going to run out of memory at the same time, right? Absolutely perfectly, yeah. Thank you, yeah. So I always do that, HA, yeah. Mostly available. Fingers crossed available. Anyway, yeah, this was a bug in TX Ring. You can find the PR for that. The solution was to turn off isolation for a compaction because it wasn't actually necessary. So that was, it took me like a year to figure this out. It was not an easy fix, but it was a good one. So.
In the data structure, you showed that you try to save the 60 bytes of a string, which is a cool thing to do. However, what's the impact or the risk for the code base? If you replace primitives, then you need to implement things like strings match prefix yourself again against your new data structure, which makes over time accumulating this, writing your own strings-like library. One good example is LLVM, where they rewrite anything from C++ vectors because they did this bit packing thingy. So what's the impact for the over time for the code base?
Yeah, so there's a PR, which somebody could look up the number. You can look at what happens in one version of this. It's a draft PR exactly so we can have this discussion. So what I've implemented is a little bit like what protobuf does. So I don't think it's kind of completely outlandish, and it's not really writing a strings library. It's like packing it. It's kind of similar to the way that the samples are packed, right? Yes, it's more complicated, and it's a PR that's like minus 1,200 plus 1,500 lines, something like that. Does anyone remember? So there's a lot of typing. I think fundamentally the usage of it is all hidden behind abstractions once it's finished. So I don't think it's too bad. But yeah, please go look at the PR, comment on it. Above all, come up with a better way to do it. That's what open source is all about. Right?
Okay, one more question, but then we're...
One more.
I checked the number, it's the PR 10991. 10991.
Perfect. Awesome. Yeah, we're going to go in the break. Thank you very much, Bryan.